In order to describe events in a physical setting, we need to establish what's called a frame of reference. The frame of reference is a set of coordinates and a clock that can be used to measure and describe events and the relationships to each other. We will be working with two kinds of frames of reference: the so-called inertial frame of reference, where Newton's laws are observed to hold, and the acceleration of that frame is zero. And the next slide is an example of this, so I'm going to let that sit where it is. And then the non-inertial reference frame is one where Newton's laws are observed to not hold, and that is an indicator that the frame itself is accelerated. Now, you can transform from one reference frame to another, usually by some mathematical transformation. And the exercise of being able to do transformations is really a critical part of the history of physics. Okay, this is the example. One of the things that I want you to walk away from physics with is a deep, deep, deep emotional understanding of why it's important to wear your seatbelts. So we're actually going to address this question in a couple of different ways. And at the same time, we're going to look at the difference between an inertial frame of reference and a non-inertial frame of reference as they describe the same point of view, the same event happening. Different points of view, same event. If you're riding unrestrained in your car at a constant speed, you and all of the stuff in your car are traveling at that speed. So you can be playing catch with yourself with a tennis ball while your friend is driving. Somebody in the back seat can pass you something in the front seat without any difficulties, because you're all traveling at a uniform velocity together. But when the car stops suddenly, such as when it has a collision of some sort, we're going to analyze this in two different ways. So from a rest frame, from the point of view of somebody standing by the side of the road, you and all of your stuff continue to obey Newton's first law, traveling at a straight line at a constant speed until you're acted upon by some outside force, such as the steering wheel, the windshield, or the dashboard, or, in a positive sense, your seatbelt. In a frame inside the car, all of a sudden some fictitious force is exerted on you by the front of the car, causing you to accelerate very rapidly relative to the car until you're acted upon by a second force that produces equilibrium, a balance, such as the steering wheel, the windshield, the dashboard, the tree outside after you've been hurled through the windshield. Any number of fixed objects can be exerting that force on you. The reason your seatbelt helps you is because it increases the time and distance that the force stopping you acts over, and therefore you have a smaller force over a larger distance. But right now we're just going to focus on the different points of view. So the car is accelerated, which is what makes it a non-inertial reference frame. Newton's first law is violated. In the first case, Newton's first law is maintained. So in the rest frame by the side of the road, Newton's laws hold. In the moving frame inside the car, Newton's laws are violated. Some types of forces. Tension, internal forces such as in a rope or a chain, and I bring these different kinds of things up because you'll see them in problems. They'll talk about tension forces, and all they mean is internal forces and the force that such a rope or chain tends to exert in a pull. The spring force is the force exerted by a spring, and this is a very common model in physics. Lots of physical systems are modeled by springs, so we use this. The springs exert a variable force depending on the amount that they're stretched. A special case of this is Hooke's law, and most objects obey Hooke's law over some set of values, and then fail over other set of values. But Hooke's law basically says force is proportional to the change in the length and opposite in direction. So the formula for that looks like this. This is a vector formula. We have the vector force F is in the negative direction of the displacement x. The constant K depends on various properties of the spring and is the same uniquely for an individual spring, but varies even among different examples of the same kind of spring. Newton's second law, acceleration and net force, right? The net external force divided by the mass gives you the acceleration produced. I've discussed this as a change model, and all this has done is add this summation of individual forces so that you have a net force. And since force and acceleration are both vector quantities, we could also write this in terms of their components ax, ay, az, so that each individual direction has a net force, and therefore each individual direction has a net acceleration. And the classic example of this, right, is gravitational force problems. Gravity acts in the y direction in a standard coordinate system only. So things fall down, so the y acceleration is not zero. Things never fall sideways, so the x direction acceleration is assumed to be zero when you're ignoring things like air resistance. This is what's known as an equilibrium condition. The sum of the net forces is equal to zero is an important equilibrium condition. There's actually a second equilibrium condition for bodies that have physical extent. This applies to point particles, but a second requirement is needed for bodies that have extent. The normal force is a force that is perpendicular to the surface, and it is a result of the interaction between you and the surface. It is incorrect to say that the normal force on you of the ground is the reaction force to your weight, because your weight is a gravitational force. The balance to the reaction force is the force that you exert on the Earth, causing the Earth to accelerate at some minuscule, negligible way. The normal force is not directly a reaction force to your weight. It's the reaction force to the molecules on the bottom of your feet, pushing downwards on the molecules on the top of the ground. It's important to keep those pairs in mind. In this case, the ground exerts a normal force on your feet that balances gravity, as in the previous example, plus leaning against the wall. So the blackboard exerts a normal force on the hand that is equal to the force that the person is pushing on the blackboard. Free body diagrams are diagrams that have only the forces on them. They should really, I suppose, be called body-free diagrams, because they actually remove the physical objects. It is tempting, and usually not fatal, although not good practice, to simply draw the free body diagram on top of the physical drawing of the setting. And what this is showing, the tension in the left-hand cable is pulling upwards and to the left, and is the thing labeled T1 in this diagram. By a property of opposite interior angles, the 45-degree angle that the T1 makes with the negative x-axis is equal to the 45-degree angle that the rope makes with the ceiling. Our T2 here is pulling up and to the right, and again, by the opposite interior angle rule, this 30-degree angle is equal to the 30-degree angle that the string makes from the ceiling, but that's a geometry thing that's not determined by the physics. T3 is pointing straight downwards, and it is equal to the weight of the object. So this drawing on the right, drawing B, makes it easier to see how the different components are going to be used in solving this problem. So the two y components have to equal T3, the x component of T1 has to equal the x component of T2, and that will produce an equilibrium.